Hi guys, and welcome to the latest video in the preliminary chemistry video series. We're looking at the topic of metals, and today we're going to have a bit of a look at the extraction of metals from their ores. Now we've kind of touched a little bit on elements and mixtures in the different spheres in the previous topic, but this time we want to have a look at ores in just a little bit more detail. So the first and most important point is that ore is a mineral which can be mined at a profit. So there's not much difference between an ore and a mineral except for the economic difference. So if we can extract it from the ground, purify the ore so that we can extract the specific mineral or metal that is common in that mineral, then we can sell that at a profit, then it's worth doing, and then that becomes an economically important ore body. So minerals which contain valuable elements, usually metals, like iron or aluminium, are called ores. And there are a couple of very important ore deposits located throughout Australia. Some of the common ores that you probably should be aware of are firstly bauxite, which is the ore which contains the metal aluminium. Galena, which contains the metal lead, usually as lead sulfide. Sphalerite contains zinc, again usually as zinc sulfide. And pyrite, and there's a couple of different forms of pyrite. Iron pyrites, which is often also referred to as fool's gold because its appearance, it looks very similar to gold, but obviously doesn't have the economic value of gold. And also chalcopyrite, from which ore we extract copper. Now there's a few other ores that are fairly important that we could add to this list, say cassiterite, from which we extract tin, and so forth. There's a large number of different types of ore bodies, and I haven't even at this point touched on things like some of the different beach sands, which may include things like ilmenite or rutile, which are sources of titanium. So we have a number of different important metals that we can extract from each of these different ores. But one of the things that we need to consider when we're looking at the process of extracting the metal from the ore is its economic value, because each of these requires a certain amount of energy, a certain amount of processing, and all of that can be expensive. So therefore, we need to have some understanding of two things. One, the economic value of the metal that we extract from the ore, and secondly, the method by which we need to extract that metal. As a consequence, we've kind of grouped metals into three distinct categories. The first category are the unreactive metals. So these are metals that are found, generally speaking, in their uncombined state. So we find things like gold and silver in an uncombined state because they're very unreactive. They don't form compounds, or they don't readily form compounds, particularly with oxygen, which is one of the dominant gases in the atmosphere. And so therefore we tend to find these metals found unreactive, probably not as often as we'd like to find them, but nevertheless found in their native state. The second type are low activity. So these ones do react. They are ones that have formed often oxides or sulfides, compounds that have been produced, and because of their low activity, they only need a limited amount of energy input for their extraction, and often the type of extraction is a clue to that. So something like smelting, which just involves heating in the presence of carbon, usually in the form of coke or charcoal, which is going to often remove, say, the oxide from the metal and leave the pure metal behind. Copper is one of the examples of a low activity metal in this second grouping. And the third type are the high activity metals. And these are the ones that require significant energy input in order for their extraction. So once we start getting onto something like aluminium being extracted from the ore bauxite, we start to move to things like electrolysis, the supplying of electrical energy in order to break the bonds and purify the metal. The amount of energy required to just pick it up or smelt it or electrolyze it increases as the activity of the metal increases. And so these are some important relationships that we need to be aware of when we're looking at how easily certain types of metals are extracted from the earth. So here's a question for you to have a think about. In the steel industry, iron is produced by heating iron oxide with carbon in the form of coke to give iron and carbon dioxide. Can you write a chemical equation for this reaction? So iron 3 oxide, so the Roman numeral 3 here means the iron is a 3 plus ion. Iron. Bit confusing, I know. The Roman numeral is here because iron is one of the transition metals and as such can have more than one valency. And where we have ambiguity, we need to use a numerical system to try and overcome that ambiguity and make it clearer. So therefore, when iron is in a compound with oxygen, and we have iron as a 3 plus, and oxygen is a 2 minus, and you can check your periodic table to check its position and to confirm that it is actually a 2 minus ion, then the easiest thing to do is just do the cross method. So Fe2O3, if you're doing it mathematically, we need 2 times 3 plus, which gives us 6 plus, and then we need 3 times 2 minus to give us 6 minus, and our compounds must be electrically neutral, so the 6 plus balances the 6 minus, and we have a compound here of Fe2O3, which I'll just write over here. Now the iron oxide is going to be heated with carbon, and it's going to form iron and carbon dioxide, which will be a gas. Now we just need to make sure that this equation is balanced. Carbon's on its own, so it's probably easier to leave that there. Now my problem is that I have an odd number of oxygens on the left side of this equation and an even number on the right. So I'm going to double this first of all. 2 3s are 6 oxygens, so then in the front here I also need a 3. I've kind of squeezed these in a little bit tight, so I'll just put the little plus here so you can see that. So 3 in front of the CO2 to give 6 oxygens, so that's now balanced. I have 2 times 2, which is 4, so I need a 4 in front of my iron, and the 3 in front of the CO2 over here means I need a 3 here. So perhaps it might be easier if I just write that chemical equation out again. Underneath 2 Fe2O3 solid plus 3 carbon solid gives 4 iron solid plus 3 CO2 gas. And there is our balanced chemical equation for the process of refining iron from its ore. Thanks for watching.